Hello, Vibrations class. For the third project deliverable, I'm going to be talking about finding a solution for the Jeffcott rotor model. So as we remember, there's a flexible spinning shaft with a mounted disc that's spinning at this shaft spin speed, omega. And this shaft is spinning about a bearing axis at a distance that's referred to as the eccentricity, which is the distance between the center of rotation and the center of gravity of this mass. So this whirl frequency can be looked at through the transverse planes of motion in the Jeffcott rotor model by neglecting torsional vibration. So these planes of motion in the x and y direction can be described as mass times your acceleration plus your damping coefficient times your velocity plus your stiffness constant times the position, and this is all equal to your mass times your omega squared times this eccentricity, which is the distance between the center of rotation and gravity. And for the x-plane analysis, this is multiplied times cosine omega t, and for the sine plane analysis, this is multiplied by sine omega t. So these are your equation of motions for your Jeffcott rotor model. So what I did to find a solution is I set these up as differential equations in my Maple program. I defined my parameters. I have a length, a diameter, I have my damping coefficient, the eccentricity, your shaft spin speed, and as well as the initial conditions for your first and second order, or for your position and your velocity in both the x and y directions. And so if you look here, I have my differential equations set up. I have my initial conditions. I have my parameters set right here, my length, diameter, mass, damping coefficient, my eccentricity, and my shaft spin speed, my omega. And then from there, what I can do is I can solve these equations of motions to get my x of t and my z of t, which are right here, solved. And then from there I can plot x of t and z of t as a function of time. And I've done it at two different, with the change in a variable. So this first one has an omega of 1. And you can see here from times 1 to 500 that at first the amplitudes are very hectic and it's a transient period, but you can see that overall as the time approaches 1,000 that it balances out. However, by changing the parameter like the shaft spin speed omega, you get vastly different results. So in this first example that I showed you, the omega is at 1, and in this example the omega is at 0.1, and as you can see, the amplitudes of these transverse equations of motion are way less frequent over the time span, which helps validate the reliability of my model.